All right, today we are diving into a classic coding problem, and we're going to solve it with a technique that is just so surprisingly simple and elegant. You'll see how two little pointers can make a really tricky problem just fall into place. So let's set the stage. Here's the challenge for you. You've got a sorted list of numbers, and you need to clean out all the duplicates. But here's the catch, and it's a big one. You can't just make a new list. You have to do it all right there inside the original array. And this leads us right to a really common problem you'll see out in the wild. LeetCode 26, remove duplicates from a sorted array. The whole idea is to change the array itself and then tell us how long that new, unique part is. So how do we even do that? The key phrase, the big constraint, is in place. What that really means is no safety nets. We can't just create a nice, new, clean array to copy things into. We have to be clever and shuffle things around inside the one we were given. Okay, so how do we crack this nut? Well, the breakthrough comes from a really cool technique that uses two pointers, and each of these pointers has a very, very different job to do. And this right here is the secret sauce. It's the reason this whole strategy even works. Because the array is already sorted, we know that if there are any duplicates, they're going to be huddled up right next to each other. We don't have to go hunting for them all over the array, which makes our job way, way simpler. You know, to make this easier to picture, let's give our pointers some names. Think of the read pointer as our scout. Its job is to run ahead and check out every single element. Then you've got the right pointer. Let's call it our builder. It's more patient, it hangs back, and only moves to lay down a new brick, a unique number, when the scout finds one. Okay, theory is one thing, but seeing it happen is where it all clicks. So let's do a step-by-step trace with a really simple array. 1, 1, 2. So here's our starting line. The very first element, the one at the beginning, is always going to be unique, right? So we just leave it there. Our builder, the right pointer, gets ready at the next spot, which is index 1. And our scout, the read pointer, also starts at index 1 to start exploring.
So the scout's first move is to look at the number where it's standing, which is a 1. Then it peeks back at the one right before it, and it asks a simple question. Is this one different from that one? In this case, is 1 different from 1?
Nope, they're identical. It's a duplicate. And when that happens, our builder does absolutely nothing. It just stays put. The only thing that moves is our scout, which shrugs and just moves on to the next element down the line. And take a look at the board now. This is interesting. The builder hasn't budged, right? It's still waiting for a unique piece to build with. But our scout has forged ahead. It's now at the very last element of the array. Okay, new position, new check. Our scout is now looking at the number 2. It does its thing again, comparing that 2 with the element right before it, which was a 1. So, are they different this time? Yes, bingo, we found something new. The scout radios back to the builder, and now it's time for the builder to finally do some work. So the builder takes that value, the 2, and copies it right into its current spot. See how it just overwrites that old duplicate 1? And only after it writes does the builder pointer finally move forward. Now the scout is at the end, so we're all done. The clean, compacted part of our array is 1, 2, and the final answer we return is the length 2.
So we've seen how it works step by step. But the real story here, the reason this is so cool, is just how incredibly efficient this is. Let's talk about the big payoff.
Let's talk time. This thing is fast. Our scout pointer, it visits every single element in the array, but it only visits them one time. That's it. So the bigger the array, the longer it takes in a perfectly predictable linear way. We call that ON time complexity. And for this problem, you really can't do any better. But honestly, the space complexity is where the real magic is. Remember how we did everything in place? That means we didn't have to create a whole new array on the side. The only extra memory we used was for our 2 little pointers. That's it. It doesn't matter if the array has 10 elements or 10 million. We call that O of 1, or constant space. And that is just the gold standard for memory efficiency. So let's just let that sink in. We solve the whole problem in one single pass through the data, without creating a new array. That's huge. It means we save time, we save memory, and the whole thing is just clean. That's what makes the solution so beautiful and elegant. Now, a good algorithm has to be more than just clever. It has to be tough. It has to work on all the weird, tricky inputs you can throw at it, the edge cases. So does our 2-pointer solution hold up under pressure? You bet it does. Look at this. What if you give it an empty array? No problem. It correctly says the length is 0. An array where everything is a duplicate? It correctly identifies that there's only one unique number. What if there are no duplicates at all? It handles that perfectly too. The logic is just rock solid. Look, this whole two-pointer thing isn't just a one-trick pony for this specific problem. It's a powerful pattern. It's a tool you can keep in your back pocket for a whole bunch of array problems. So the real question to ask yourself now is, where else could you use this idea of a scout and a builder? Thinking about that is how you really start to master the technique.